Okay, so the final speaker of the morning session is Sasha Hinkley, who's going to talk about sparse aperture masking with ELT.
Okay. Great, thank you. There we go. Good. So it's possible many of you don't know me. I'm Sasha Hinkley. I'm a professor at Exeter, and it's a real pleasure to be here. I'm going to talk about just some work I've been doing related to sparse aperture masking on the ELT, roughly in the context of the METIS instrument, which I'll talk about. So this is a talk primarily about extrasolar planets, primarily, and I'm the only thing keeping you between lunch. So hopefully you're interested in exoplanets enough to stay long enough to hear me. So we're really learning a lot about extrasolar planets in the last few decades, but really we're getting into the area of characterization now, and especially through direct imaging, which is an area I work on quite a bit. And the thermal infrared is really going to be the sweet spot for characterizing extrasolar planets through direct imaging. So as a good example of this, this is a plot of some theoretical models, compositional models of the composition of the atmospheres of a well-known exoplanet, HR 8799. And the band average brightnesses for each of these three sets of models can be seen by these horizontal lines. And so as you can see here, from 1 to 2 microns in the JH and K bands, these models are basically indistinguishable from a broadband photometry point of view. But when we go and look at the same set of models in 3 to 5 microns, these models really differentiate themselves clearly. And these models have really dramatic differences. These are really orders of magnitude shifts in the CO to CH4 ratios, for example. So we really need to go to the 3 to 5 micron realm to characterize extrasolar planets and say something really powerful about their compositions. This is closer to the peak of their black body distribution, but for these reasons also this tends to be the most important area to characterize extrasolar planets. And we really haven't done that yet. Sphere and GPI, as I show here, are really operating here in the JH and K bands. And the kind of images that have come from sort of first generation instruments like Keck that were using instruments that were not dedicated for the purpose of extrasolar planet imaging might look something like this. This is one of the early K-band images of this now famous system HR 8799 that Rick talked about. But when we look at the same system in the L-band at 3.8 microns, you can really see these planets tend to stand out from the star a little bit, and you can even see this innermost planet E quite clearly if I go back and forth. So 3 to 5 microns, in addition to what I just mentioned about the power of being able to say something about their composition, these planets just tend to be brighter in these regions, and 3 to 5 microns really gives us greater sensitivity to these warm, young exoplanets at small orbital radii. So why don't we just do this with JWST, you say? Well, we're going to do this with JWST. There's an early release science program that just got approved a year or so ago. There's a number of us working on this, about 120 team members are working on this, and we were given 52 hours to basically do a study of a handful of extrasolar planets with JWST. And this is really exciting because along with the initial GTO observations, this is really going to be the first observations of extrasolar planets over their full luminous range. We've really just seen the tip of the iceberg at sort of 1 to 2 microns so far. An example of the image that we chose for this program is HIP 65426b. This was a wide separation planet that was discovered with Sphere. The Sphere image is shown here in this left panel. It's at half an arc second or something. But when our simulations of what this might look like at 4 microns and even 15 microns are shown here. And I show this because I think this makes the point that the resolution of JWST is not going to be great. JWST really suffers from this, but like Rick said, it has powerful sensitivity. JWST really, the resolution, the implications of that is that it really prevents us from studying the zones of planet formation. And you might say, big deal. Why do we want to study the zones of planet formation? Isn't it good enough to just study a planet out here where it was probably ejected or dynamically moved out there after 10 or 20 million years? Well, I claim that we really want to image these planets as early as possible because the planet formation process is incredibly complex. And if there's any transit or radial velocity people in the audience, I'm sorry if this comment offends you, but the direct imaging method for studying exoplanets is really going to be the most powerful mode for saying something about the formation of extrasolar planets. A good example of that, I think, is shown by this plot here. This is a model, these are theoretical models of the brightness of a collection of 1, 2, 5, and 10 Jupiter mass planets, I guess, as a function of their age. And there's these two competing models that are shown here, the so-called hot start shown in red and the cold start shown in blue. And you can see out here at sort of giga-year type ages, these models agree very, very well. But there's a huge discrepancy in our understanding of the early thermal histories of planets at the early times, out here at just a few megayears. This has to do with a whole host of complicated reasons, like the initial shock physics of the accretion of gas and dust onto these planets. It's incredibly complicated. So what we'd really like to do is be able to observe as many extrasolar planets at the youngest ages as possible to say something about the thermal histories of planet formation. So, great, but to study these newly formed planets at just a few megayears, we really need to reach the zones of planet formation, obviously. Sort of 3, 4, 5 astronomical units. We think that this is where the core accretion process takes place, forms a massive core, accretes a huge envelope of gas. We think this is how the formation of these massive planets happens. So we want to get to these planet formation zones. Why don't we just observe a bunch of closer stars? This is a meeting about high resolution, right? So let's just, how do we maximize our resolution? Let's just observe a bunch of closer stars. So this may not be obvious to people in the room that don't work on direct imaging, but if we just make a list of stars that are reasonably close, that are still very young, it looks something like this. And I'm going to walk you through this table. I like this table. It was made by Joel Kastner, and I borrowed it from him. This is actively accreting T Tauri star systems within 100 parsecs. These are the youngest stars within 100 parsecs. And if we just look at this table carefully, I'm going to highlight a few stars here. There's a handful of stars here that are at ages of 15, 20 megi or something like that. The planet formation process is long since over at these ages. Planet formation happens in the first few megayears when the gaseous disks are still present. So let's just ignore these. Let's cross these out of this table. Let's keep looking at this table a little more. I'm going to highlight these systems here at 97 and 100 parsecs. There's about 4 systems that are at 100 parsecs. This is really getting too distant to image the zones of planet formation at just a few AU. Okay, so let's cross those out. And what we're left with is 3 stars. So what I'm telling you is the number of nearby stars that are fairly young, that are optimal for doing a direct imaging survey, is 3. This is obvious to anybody who works on extrasolar planet direct imaging, but it's probably not obvious to most people in the room. And if you look at the sort of sensitivity of recent direct imaging surveys of extrasolar planets, it looks something like this. So this is a completeness map in this mass in terms of Jupiter masses versus semi-major axis space. This is a sensitivity curve that I got from Arthur Vegan, who published the results of the NACO large program a couple of years ago. And they were very sensitive out here to sort of, out here at 100 AU or something. And this is the 95% confident completeness contour. And so, they are sensitive into this region, but this hopefully just makes a point. I'm going to come back to this plot in a moment. Our best bet then for studying young stars that are hopefully not too distant is probably the Scorpius-Centaurus association. And it turns out that a handful of the directly imaged planets have been imaged in this association. This is the closest OB association. It's at about 140 parsecs. I like this plot from Aaron Rizzuto because it shows where on the sky this collection of stars is. You can see the Scorpius constellation right here traced out in red. So this is really probably our best bet. But like I said, it's at 140 parsecs. And that's the best we're going to do to to sort of maximize our resolution when imaging a collection of young stars. So at this distance of 140 parsecs, the kind of zones where we think the cores of these massive planets form at about 3 astronomical units, that corresponds to 20 milliarc seconds. Okay, I'll just save you that quick calculation. Okay, and this just so happens to be about the diffraction limit of the ELT operating in the L band. The point here is that if we want to image these very young planets in the zones of planet formation, we're going to need a technique that gets us within the diffraction limit of the future largest ground-based telescopes in the near infrared. Okay, so how do we do that? people are probably aware of this technique, but I'm going to talk just for a moment about sparse aperture masking. We've been doing this for several years now at Keck and also VLT. The task here is you take your 10-meter telescope, you throw away 95% of the photons, and you turn your pupil into a collection of little interferometers. And you do some techniques that were pioneered through radio astronomy to get detections of things within the diffraction limit. Some sensitivity within the diffraction limit. Not a ton, but some. And I can show you just how much that is. So the results of what this kind of sparse aperture masking has done over the last sort of 5 or 10 years, I think it'd be pretty well summarized in this plot. This is, to my knowledge, this is the only plot that shows the distribution of companions for fairly young stars, 5 to 10 megayears, for stars a bit more massive than the sun, sort of 2 to 5 solar masses or so. And we can see in this mass versus orbital separation plot, again, we can see the early results from interferometry up here. These are probably stars, low-mass stars. Here's sort of conventional AO imaging out here at sort of a few hundreds AUs. But the work we did at Keck and VLT discovered sort of a population of stars interior to, a population of companions interior to that. I'm not going to call them planets. I'm not sure what a planet technically is, but we found this sort of small population of companions that seems distinct from the other methods of detection. This is a particularly interesting region of parameter space because it's sort of reminiscent of these directly imaged planets that I show here in brown. It's sort of a scaled up version of those. But this is so far out of reach to these other images, like other techniques like interferometry and AO imaging. So I think the sparse aperture masking results from Keck and VLT over the last decade or so are extremely promising. And the question then, to my mind, is what can we do on the ELT with an instrument like METIS? Now, Rick mentioned his instrument, Mikado. METIS is one of the 3 first generation ELT instruments. Delivery and power and all that's probably changed now. It's probably a bit later. This is the only instrument that's operating redward of 2 microns, so it's going to be an L, M, and N band imager. And the UK is actually contributing an L and N band high-resolution spectrograph. So this will be the 3rd of the first generation instruments, and I just simply asked the question, what can we do if we put a sparse aperture mask on this instrument METIS? Which has the advantage of being able to operate in the L band, and I just told you a few slides ago that that's the sweet spot for imaging extrasolar planets. And sparse aperture masking will really take full use of the 39-meter aperture, which you really want to do if you're going to spend €1 billion building this observatory. So I just did a simple exercise. I basically selected a set of stars from the Scorpius-Centaurus star-forming region that I just told you a moment ago. I guess I selected something like 55. Most of these I chose closer stars, sort of 120 parsecs or so. And these have ages between sort of 16 megayears or maybe 10 megayears. I just asked the question, what can we do? So I showed you this plot a moment ago showing the sort of state of the art, if you will, for AO imaging, the completeness curves of the NACO large program. And if we just think about, sparse aperture masking aside, if we just think about what we can do with classical coronagraphic L-band imaging on the ELT with METIS, the parameter space looks something like this. So as to be expected, since these planets are brighter at L-band, for a given contrast, you're able to reach deep into this planet regime out here. But we're still sort of limited into the zones of planet formation, which is in here, where we'd really like to be able to study these. So I basically took our contrast that we achieved at Keck and VLT. That's just a plot of contrast relative to the host star versus angular separation in milli-arcseconds. And you can see here's the Keck diffraction limit at L-band. And you get some sensitivity within the diffraction limit. Not a ton, but some. And I did the most naive thing possible and just scaled this contrast based on the improved resolution of the ELT and some arguments for enhancing the sensitivity. And I took a straw poll of the experts in the field, and they think this is pretty reasonable, possibly pessimistic for the kind of contrast that the ELT will achieve using sparse aperture masking in the L band. Okay, fine. So what would it look like if we applied this contrast shown here in red to this set of 55 actual stars in SCO-SEN, and we get something like this. So the red contours, the red completeness here shows our completeness to objects within that are getting close to the sort of ice line regions, the sort of ice, the zones of planet formation where we think these planet forms out here, just a few astronomical units. And it's worth saying that really sparse aperture masking is the only sort of technique that can do this. So I did this exercise and then I asked, well, wait a minute, what about a shorter wavelength? Couldn't we just probably achieve the same thing if we took maybe Rick's instrument Mikado and did the same exercise at something like H-band? And I did the same, I just basically took a contrast for Mikado and did the same thing. And what we find from Mikado is something like this. I didn't know what the results were going to be, but this is what I find. I find that Mikado really does have excellent sensitivity in here at just sort of even just less than 10 astronomical units or so. And this is just due to the really impressive angular resolution that Mikado will achieve at H-band. I chose H-band because that's sort of a medium between good resolution, but also sampling these sort of thermal properties of these planets. So I guess what I'm arguing here is that I think there's a place for sparse aperture masking to really get into these close angular separations and really complement the kind of work that things like Mikado will do. And also METIS with conventional coronagraphic imaging. It's worth saying also that only the ELT is going to be able to get this close, just due to the superior resolution. GMT is not going to be able to do this, the Giant Magellan Telescope. And basically, I didn't realize that until a member of the GMT consortium pointed that out to me at a meeting. So that's what I say here. So I know that I'm keeping you for lunch, and I just want to have one final point. This is a meeting about high resolution, and I think I just told you that high resolution is great for getting into these zones of planet formation close to the star. But really the implications of this are it opens up a huge number of additional young targets to study. This is a really overlooked point about high resolution in high contrast imaging. So what I did is I just made a little table, and I asked the question, for how many stars, if we just took a coronagraph and put it on the ELT with something like METIS or Mikado, and we asked the question, how far out in volume can we go such that we can basically access the snow line around nearby stars? And if you just do a calculation for the diffraction limit, it turns out that if you go out to about 40 to 60 parsecs, you can still access the diffraction, you can still access these zones of planet formation. So what does this mean in terms of number of available targets? It probably means you can access these young nearby stellar associations like TW Hydra, Tuckhor, Beta Pictoris. These are sort of ages of sort of 10 to 100 meg-years or so. And this is maybe 100 stars. This number may go up with Gaia, but that's certainly a correct order of magnitude about the number of available young stars. But if we were to include a sparse aperture masking on METIS, we would be able to achieve the same angular resolution, but at a much greater search volume. So what we find is that this allows us to go out to 140 parsecs and still access the snow line where these planets form. And the implications of that are really dramatic because this allows us to access these star-forming regions like SCO-SEM, Scorpius Centaurus, that I just told you about, and also Taurus at these extremely young ages of 1 to 10 meg-years. And this has the opportunity of opening up thousands of targets for us. So this is an overlooked aspect of high resolution that I wanted to mention at this meeting. I'll wrap up and let us get to lunch and just sort of summarize my points. 3 to 5 microns, this is the future of exoplanet imaging going forward. JWST is not going to do a very good job of this. It's going to have great sensitivity, but it's not really going to have the resolution to say something powerful about planet formation. So I think sparse aperture masking on an instrument like METIS is going to reach sort of 2 to 5 astronomical units around thousands of stars potentially, if you can get the observing time. And this is really going to complement conventional L-band coronagraphic imaging as well as H-band imaging on something like Mikado. And I'll leave it at that.
Is there any questions?
Sasha, the extent to which you're going to reach into the zones of interest depends upon the higher contrast you think you're going to get with the masking, going from 5 magnitudes of contrast to 8. How do you think you'll get that on ELT, given that few interferometrists think they're going to get delta M of 8 with their next generation of interferometers?
Yeah, so the thing that limits your, as you know, better than anybody probably, the thing that limits your contrast with sparse aperture masking is your ability to basically calibrate your closure phases that you measure. And as I had conversations with people like Peter Tuthill and Mike Ireland about this, about how to come up with a scaling factor for this contrast. And they basically convinced me, and they said that the most naive thing, that if you can calibrate the closure phases comparably between something like Keck and VLT and the ELT, then the contrast should scale with the ratio of the apertures. So the assumption that I'm making here is that when we do sparse aperture masking on the ELT, we will be able to calibrate the closure phases to a similar extent than what we can do here at Keck and VLT. Now, there's a lot more mirror segments on the ELT. There may be things that I'm just naively overlooking, but I think for now, this is the most naive sort of scaling that we can do. I've been told, I think the experts that I polled on this, on sparse aperture masking, half of them told me I was being optimistic. The other half said, you're being way too pessimistic. So what I chose is the sort of naive, happy medium there. I should say, we did achieve 8 magnitudes of contrast using sparse aperture masking, but we had to throw a half a Keck night at HR 8799. And when we did that, I think those are the deepest limits that have been published with L-band sparse aperture masking, and this is my 2011 paper, I don't remember which, but these were the only measurements of companions within about 3 AU of the HR 8799 system, and we got down to sort of 10 Jupiter masses or so, and to do that, we needed to achieve 8 magnitudes of contrast at 1 lambda by d. So I think, but we had to throw half a Keck night at it, as I said.
Yeah, my question is kind of similar. In your plot of the 95% limits, you seem to be gaining something like a factor of 4 or 5 in inner angle from going from the coronagraph to the sparse aperture mask. And so I'm just wondering where that factor comes from. Because you're more than 10 AU in the coronographic imaging,
yep.
and then
So
you're down to something like 2 AU.
Yeah, so that's the blue. So where does the improvement in resolution come from? Boy, there are people in the audience that could answer this better than I could, but essentially, in a full aperture, you've got a lot of short baselines that are degraded.
Sure. Yeah. But you get a factor of 2 from the sparse aperture mask, and so I'm just wondering how you get a full factor of 4 or 5.
I guess you'd have to look at how the apertures, the baselines in your sparse aperture masking contribute. You're weighting the longer baselines more significantly than you are in the conventional full aperture. It's not clear to me why that would come out to a factor of 2, but probably no doubt depends a little bit on the mask design and the distribution of the baselines that you'd find. You guys happy with that back there?
There's a factor of 2 from interferometry, basically.
Yeah.
Okay. You mentioned the sweet spot is 3 to 5 microns. Is that still true from space as well? Or do you get when you go to short wavelengths from space, would that be worth doing? I'm just thinking shorter wavelengths means your inner working angle gets smaller, basically.
Mm-hmm. Yeah. So I think what we're really interested in doing is we're interested in understanding what the full luminous range of these extrasolar planets look like. I agree with you that if we observe at 1 to 2 microns with JWST, I don't know why you'd want to do that, but if we observe it with JWST at 1 to 2 microns, we could get a better inner working angle. But I think we'd be missing this whole question about what does the spectral energy distribution of these Jovian mass planets look like at 5 microns or 10 microns? We just don't know. The models there are horribly inefficient, or horribly unclear. And the person who told me that was Isabel Baroff, my boss at Exeter. And she's the one who makes these models at 5 and 10 microns. So she was thrilled when I told her we got this JWST time to do this, because there's going to be a day of reckoning at Exeter when we find what the spectral energy distributions of these planets look like at 5 to 10 microns, and I'm going to go down the hall and compare them to her models. So yeah, I guess it's a scientific trade-off is my answer to your question.
Okay. Thank you, Sasha.
Thank you.